Welcome to this video presentation on extended surfaces, commonly known as fins. Today, we'll be working through example 3, which focuses on analyzing heat transfer in a rectangular fin. Let's look at the problem statement. We have a fin that is 5 millimeters thick and 45 millimeters long. Its base is on a plane plate maintained at 125 degrees Celsius. The ambient temperature is 25 degrees Celsius. The fin material has a thermoconductivity K of 55 watts per meter degree Celsius, and the heat transfer coefficient H is 145 watts per square meter degree Celsius. We need to determine three things. First, the temperature at the end of the fin. Second, the temperature at the middle of the fin. And third, the heat dissipated by the fin per meter width. Now let's begin with the solution by outlining the given parameters. The length L of the fin is 45 millimeters. The width B is 1 meter, since we are considering per meter width. The thickness Y is 5 millimeters. Thermoconductivity K is 55 watts per meter degree Celsius. The heat transfer coefficient H is 145 watts per square meter degree Celsius. The base temperature T naught is 125 degrees and the ambient temperature TA is 25 degrees Celsius. Now, for part 1, our job is to find the temperature at the end of the fin, which we are calling TL. Now, we assume that the heat loss by convection from the end of the fin, under this condition, the temperature at the end of the fin is given by the temperature distribution formula for a fin with a convection at the end of the tip, as indicated there. That is the formula that we need to work through. So when x is equals to L, the formula simplifies to theta over theta naught equals to T minus TA over T naught minus TA into the holistic formula we see there, which has the hyperbolic cosine. And this can be simplified to the second part of the formula, which you're seeing there, TL minus TA over T naught minus TA, which is equals to 1 over cosine ML plus H over KM, hyperbolic sine of ML. Okay. So before we proceed, we need to calculate the parameter M. This parameter M is given by square root of H times P over K times ACS, where P is the perimeter, ACS is the cross-sectional area. Since the width B is much larger than the thickness Y, so 2Y much less than 2B, the perimeter can be approximated as 2B, and the cross-sectional area is B times Y. So this simplifies M to the square root of H over K times 2 over Y. And when we do that, we end up with a value of 32.47. Now let's calculate ML based on that, and we get a value of 1.461. And if we plug into the formula, which we have done, it gives us the results that we're seeing there. And finally, we end up with a value of TL equal to 66 degrees Celsius when we plug in the values and calculate accordingly. And this 66 degrees Celsius is the temperature at the end of the fin. Now for part 2, we need to find the temperature at the middle of the fin, which we are calling TL over 2. Now we use the same temperature distribution formula, but this time x is equals to L over 2. And this equation can simplify as shown on the screen. So then once we now start plugging in the values which you got from the previous calculation. The calculation proceeds as follows until we end up with the value of TL2 equal to 80.14 degrees Celsius. This is the temperature, the middle of the fin. Now for part 3, we need to calculate the total heat dissipated by the fin per meter width, denoted by Q fin. Now the formula for total heat dissipated by a fin with convection at the tip is given by Q fin, which is equals to square root of P times H times K times ACS times T naught minus TA multiplied by the term we have the hyperbolic tangent of ml plus h over km divided by 1 plus h over km times hyperbolic tangent of ml. Now for a rectangular fin, perimeter P is approximately 2 times that is B plus Y, and the cross-sectional area ACS is B times Y. So substituting this into the formula and plugging in all the numerical values, the square root of all the values as we have we plug in, we end up with a calculation as such, and finally we are able to get Q fin, which is equivalent to 816.9 watts per meter width. And this concludes our detailed solution for example 3. Thanks for watching. If you found this video helpful, please consider subscribing to our channel for more content like this. Don't forget to hit the notification bell so you don't miss out on our latest uploads.